the circuit board's really sharp, and if I don't wear a glove, I'll cut myself. It's not that it's like very delicate or I'm going to do any magic or anything like that.
That's for electrostatic stuff.
No, it's not for ESD. This doesn't have a power inlet, so we're all good. Okay, ready? Do you want to come a bit nearer? So I thought I'd just do a bit of a reveal and show you what's inside a dCS Lina DAC. So this is my constant travel companion, Lena. She goes with me all over the world, and this is what she looks like inside. And there were a couple of things about the way Lena is made that I wanted to show you guys. So, first thing I wanted to show you is that most of the electronics that you'll see here at this show, the chassis are boxes. And what I mean by a box is something that's made out of flat plates, okay? Or maybe folded plates. So the chassis of the Lena is milled from solid billets. So this is the bottom plate. This started life as a billet of aluminium this thick, and then it's been milled out to make this shape. You can see the milling marks here, but you can't actually feel them. It's completely flat, but you can see where the milling machine has gone around, okay? Now, so this has a number of benefits of using this way of constructing. Firstly, you can hear, this has a very, very low resonant frequency. If you make the chassis from flat plates, the resonant frequency is much higher. So this is much more inert. The second thing is we can make it exactly the shape we want it to. So in this case, you imagine this is upside down. So the circuit board is sort of folding around the transformer here, and the transformer is a potential source of noise, both mechanical and electromagnetic noise. So we want to move the transformer as far from the circuit board as we can. So what we've done is, instead of having feet screwed to the outside, we've actually used the milled construction to drop the floor where we mount the transformer, which brings the transformer further away from the circuitry that can be affected by it. This part of the circuit board is the the power supply. So this is all the regulators and everything that take the voltage from the transformer and smooth it out into really nice DC. That can generate quite a lot of heat. So what we've done is we've mounted it directly against the chassis, which is the milled chassis. So it's quite thick. It's probably 3-4 millimeters thick. And this whole part of the chassis, which is again milled from one solid billet, this is all heatsink. The entire chassis is a heatsink. So we don't need any discrete or external heat sinks. The whole of the chassis is a heatsink.
I was wondering why you didn't short circuit for you. I was looking at it.
So another advantage of this construction, let's say we had something this side that was very sensitive to electromagnetic interference, and we wanted to put a shield in between them. Well, instead of putting a separate part in, we can just mill a wall into the case and put that the other side of the wall. So we can basically configure the chassis around the needs of the circuit. If you look at this end plate here, spacers, which you would normally need to mount a circuit board in a box chassis, these are milled into the end piece. Not only milled in, but they're pre-drilled and they're pre-tacked, so I can put a bolt in. I don't need a nut. I just have the bolt and I put it directly into the chassis. So you can see all the mounting points, all the screw holes, they're all built into the chassis. So the number of pieces I need in this construction is much lower than if I'm screwing plates together. If I have two plates like this, and I need to put a bracket to hold them together, and then I need 2 screws on each bracket. And if I want to mount a circuit board, I need spacers, which are like little turrets. that I put the circuit board on, and a bolt goes through and a nut on the other end. Here I can just mill the spacers into the chassis. So that's about the chassis. If we look at the circuit board, so sharp. So looking at this, you might think that this is 6 separate circuit boards. This is one circuit board. This is called a flex rigid circuit board. So basically, this is a 12-layer board. So there are 12 layers of conductors inside this, and then there's this solid substrate. What this manufacturing technique does is it removes the substrate around these edges, and then the 12 layers of copper traces are encapsulated in a flexible resin, which means that the whole board can now bend. So we can take a 30 centimeter by 50 centimeter board and we can fold it up and put it inside a shoebox. The other benefit of this, from a packaging point of view, is we can take advantage of these features. Like I can fold a heat generating component. I can fold it up to a thick bit of chassis and mount it directly so that it can use it as a heat sink. Or if this is very sensitive to noise, I can fold it down behind a wall that I've built into my chassis. So the combination of the flex rigid board and the milled construction gives you really, really interesting packaging alternatives. The second area where flex rigid gives us enormous benefits is electrically. So anytime you have two conductors meeting, you get an impedance mismatch between the two materials. Because this is one piece, every one of those 12 planes is completely uniform impedance, which means electrically this board behaves nearly perfectly. It behaves just like the SPICE model. There are no impedance mismatches because we have two wires connecting together, or we have a ribbon connector.
The board has how many layers?
12.
12 layers?
12.
Wow.
This ribbon cable is actually
Is 12 layers of conductor inside a piece of resin.
It's really inside, so it's not additionally soldered on or anything.
No. This is one board.
Just one board.
Yeah.
I thought it was ribbon cable.
Yeah, exactly. That's why I'm explaining it, because when I saw this, I thought these are ribbon cables, but it's way cleverer. So a ribbon cable, if any of you have seen a ribbon cable close up, a ribbon cable connector consists of pins and like a spring that goes down on them. So the spring can fatigue and it grips less loosely. There can be gaps. The pin can get oxidized, or there can be dirt. So anytime you have a physical connector, you have a potential point of failure. With the flex rigid construction, we have so many less potential points of failure, because this entire board can be tested as one unit. We don't have 6 boards that we need to then assemble together and then retest, system test. So this can be tested by the board manufacturer, and when it's delivered to us, we know 100% that it's working. So the most interesting thing from my perspective is the flex rigid construction, especially with this size of board. There are very, very few board manufacturers who have the machines that can stuff a flex rigid board this big. It's very specialized, it's very new. I think we're the only audio company that's using flex rigid at this point. So this is a much more expensive way of building a board than if we use separate boards. The milled construction from solid is much more expensive than using flat plates and bolting them together. But with this construction, we can use one bolt size with one torque setting. We need no spacers, we need no nuts, because they're all built in. And the time that we save assembling the product, our previous generation of products took 3 days to assemble and test. This takes 15 minutes to assemble and test. And the saving on the human costs more than offset the additional costs of the components. So by making it in a much more sophisticated way that uses much more expensive components, we've actually made the product cheaper.
How much is this?
This Lena DAC is 20,500 sync. This is our entry-level product.
If you have a problem with one of the connectors,
This is not a connector, it's just a trace.
yeah, it's flexible PCB, right? They call it.
Yeah.
Yeah. So if you have one problem, it's cracked or something, then you have to throw it away.
Yeah.
You can't be repaired.
No. But the failure rate with these boards, once they've been tested by the manufacturer, we've been selling this product for I think 2.5 years. I don't think we've ever had a failure. They are incredibly reliable because there is just nothing to go wrong.
Yeah. Flexible PCB is a new technology.
Yeah, it's really exciting technology. So happy to answer questions. That was what I wanted to show you. So the milled construction, the flex rigid boards, and what you get when you combine them is really, really powerful, really exciting.
These are resistors, right?
Yeah. So this is actually the DAC.
Oh, so it's R2R DAC.
It's an R2R DAC, so 48 resistors per channel, and then the dCS kind of magic, if you like, our proprietary advantage or uniqueness is the way we use these resistors. We basically, we have 48 per channel, but the signal that's being passed through them is upsampled to 5-bit 2.8 megahertz. So for maximum signal, we're going to light up 5 of these resistors. The reason that we have 48 per channel is because we want to move the signal around more or less randomly so that we're distributing the current statistically over time, distributing it evenly among these resistors. And so we have like a brain, which is for every sample is deciding which and how many resistors to light up. That's running in this FPGA, and the algorithm is called the mapper. And this is like the brains of the ring DAC. Every single sample is being sent to a different combination of these resistors, which basically means that signal correlated distortion is being turned into non-signal correlated noise. It's the job of the mapper. And rather like the background noise in this corridor, your brain is able to filter it out very easily. You're focusing on my voice is the signal, and the noise is easy to ignore. Whereas if I introduce distortion into my voice by holding my nose, that's very difficult to ignore. Your brain can't filter that out. But all the background noise, because it's not correlated to my signal, it's very easy to filter out. So we're trying to, and noise can be mathematically noise shaped. You can kind of move it around, hide it in the corner where nobody's going to notice it.
Does this act as a shield? Or?
That is a shield around the track. It's a toroid in there. So this is just a shield.
I see there's an SD card there. Is this an SD card?
Is it?
Yeah, it's a micro SD.
Yeah, it's a micro SD. So that's the no. It could be actually for the firmware. Though I mean the firmware.
Update.
Yeah, probably.
Firmware update.
Yeah, come to the update thing.
Yeah, 16 gig.
dCS has been famous. You guys can always update your normal deck. You can send in for an Apex update and all these things. And this guy, I think basically you can't, right? Yeah, since it's already on the board.
Well, because it's flex rigid.
Yeah, so you can't upgrade the deck.
No, exactly, because the DAC is this part here. The Apex board is essentially replacing that part. This is half Apex. So this...
I hope at buying this because all the other product was upgraded Apex.
Yeah. But so
waiting for this guy to go full Apex.
Yeah. So well, it's halfway there because both this Lena DAC and the Apex upgrade were results of the R&D work done on the Veres.
Yeah.
So Veres is the project is moving along, and then the first branch eventually becomes Lena. The second branch becomes Apex. So the first branch already has some of the R&D that went into Apex, but not all of it, because Apex came afterwards.
It's investment here, so I was thinking, wait for you guys to go full Apex,
Yeah, maybe we will.
Because it can be upgraded. The other deck all can be.
It can be. We just need to swap the whole board.
Yeah. Expensive then.
Yeah.
I saw that your Rosina and all the other deck can be upgraded, with at least partial.
Yeah,
Not
but
expensive.
but as I say, there are like 16 good reasons why we went with flex rigid construction, and
I like
it's like everything. It has
IT line also. It is great. Yeah, I know. It is great.
everything has advantages and disadvantages. This is less modular, but in terms of the improved yield, we get no test failures. We get very so far I don't think we've had a single one that needed to come back to the factory. So it's very resistant to failures. Gives us the packaging advantages, the ability to utilize the milled construction much more flexibly. So and the electrical advantages of common impedance, the uniform impedance.
So it's half apex.
Yes,
some of the
yes,
technology figured out.
more or less, half.
Those OCX or is it just normal?
No, so the clocks, this is the DAC,
Yep.
so the clocks in the DAC are both VCXO because we have VCXO, voltage control.
Yeah.
So in the master clock,
you have-
we have one OCXO and one VCXO.
I always curious, isn't a better clock in a deck better than an external clock? I just, sometimes I don't get it.
No, so excellent question.
Yeah.
And the answer is that the clocks are like a conductor in an orchestra,
Yeah.
beating the time.
He's the last guy. Yeah,
Yeah, he is governing him.
Yep.
This is the mapper. He's making the decisions which resistors, and he is telling him now. These clocks always manage the digital to analog conversion. Always. Even if you have a master clock.
That's why I say this is a 3-piece design. I was considering this set for a long time. So it's 3-piece design. I always don't get it. If the DAC clock is good enough, why do we need a master clock?
So the DAC, the
Nearer anyway.
let me answer. So the clock in the DAC is absolutely as good as we can make it, but it has an FPGA next to it, running at 6 megahertz. Okay, it has a transformer. It has all this circuitry around it.
Okay.
In the master clock, we have been able to scale down the environment to only what's needed for the clock crystals. So even if we use the same crystals in the master clock, we don't. We use one OCXO and then one VCXO. But it's the same as this VCXO. It's exactly the same crystal. But the environment that it's running in is so much better.
Yeah, there's an advantage there, but then the cable loss?
No.
I mean, the clock cable loss?
It's a TTL signal. We can recover it perfectly with the PLL. The fact is, it's a less jittery clock. We're not sending the clock signal over an audio interface. It's not embedded in audio. We're just sending a TTL square wave.
One of these RJ45 connector, right? Is it? I mean, you got two.
No, it goes through the BNCs.
Oh, the BNCs.
Yeah, just a 75 ohm BNC. So the fact I mean, you can hear the improvement. I can play you upstairs. They have the master clock in the
I hear it. I hear it before at their show.
So start playing a track with the master clock, and then just pull the cable out in the middle of the track, and then put it back in. I do this at shows, and you can immediately hear the difference
that
it's
is
making.
the amazing part that technically is very hard to understand.
Yeah, but the main thing to understand is these clocks are always the ones in charge. The master clock just puts a hand on the shoulder and just steadies these clocks. These clocks.
So your design is different because the rest of people design, they just cut off these two clocks and then they use the external clock.
I don't think you can do that. I can't speak for other people's designs. But
what they do is that they also using the master clock. They do a PLL or whatever. They do it, and then after that it's 10 mega. Then they come in and then they just drive the thing.
Yeah.
There are people who do that.
We've been doing clocking for 30 years.
So you guys are specialists. There is a chance that we ask you this question because you are here.
Well,
so now I learned something. You do something different.
Yeah. But trust me, these clocks are always in charge.
Yeah, you guys do something different than your clock works. Yeah.
And these clocks are very, very accurate clocks, but there is so much going on in this chassis that there will be a little bit of EMI which will be affecting them, which we can eliminate in the master clock, just because it's in its own chassis. Clock crystals are incredibly sensitive to mechanical vibration, temperature fluctuations, EMI. They're sensitive to everything. They're like they're like the most sensitive woman you've ever met. They break out crying at the least thing.
Vibration is the worst of everything.
Yeah. Well, and temperature. I mean, the resonant frequency of the crystal changes for every tenth of a degree.
dCS is always so expensive. It's also a mystery to every one of us that we never got a chance to try it. So this is the most basic entrance level thing that at least I dare to ask questions.
So you're saying that the master clock and this clock, you have some circuitry to take in the master clock and with this as a reference, still as a reference, and do some compensation to correct it.
Exactly. That's why. That's
interesting.
So that's why we use VCXOs. VCXO stands for Voltage Controlled Crystal Oscillator. So you can change the resonant frequency, you can tune the resonant frequency of this crystal by changing the voltage. If we used OCXOs here, we wouldn't be able to use a master clock, because they're always at the same frequency because they're tuned by temperature, and they have a resistor inside them which has something. There you go.
So you're playing around with the voltage
exactly. So we're
benefit from the master clock.
The voltage that is driving these is what's tuned by the master clock.
That is different from other people. Exactly. Other people just don't do it. Yeah.
I thought it was obvious.
No, they don't.
I don't know whether they do it.
Most of them, they just chop off the clock and then just take the external clock. And then they go through some flip-flop and then just generate back the master clock, MCLK or the ACK something. They just generate back. Yeah. It's different.